Okay. And with this slide, it's got a lot of details, but I would like to say that one of the biggest uncertainties has to deal with modeling the isotope ratio value of the evaporation off soils. Soils are quite complex. They're porous media. If you want to go out and empirically determine what the evaporation signal is, you could maybe put a chamber over bare soil and do it that way, or you can collect the soil water and apply a Craig and Gordon fractionation model to that. And that's what's normally done in these studies. But then you have to decide what water in the soil is the evaporation water, right? It's easy if you have a lake, you just get the water from the surface of the lake. That represents the evaporation surface. But in a soil with a drying front, you can start scratching your head thinking, well, where is the evaporation coming from as the surface gets dry and the wetting front starts to move down in the soil profile? You have to be aware of this. And so it's kind of a feature of these studies that is still a bit uncertain. And one of the big uncertainties has to do with this kinetic isotope effect of diffusion. Because the kinetic isotope effect in a turbulent surface, like right at the boundary layer of an open body water, is going to be different than the magnitude of the kinetic isotope effect of water diffusing through a porous medium. And so getting the kinetic isotope effect right is really important here. So that's still an area of uncertainty that needs to be worked on, and better models need to be developed to know what water to collect and what isotope kinetic factors to apply. Okay, so an example, we did some work a number of years ago now in Morocco. We were invited over to do some work in the King's olive orchard in Marrakesh. It was quite the deal. And we set up an eddy covariance tower and collected air samples from a profile in this vegetation. And back then we didn't have lasers, and so we used the very old school cryogenic trapping method. We pulled air using a pump down from different heights of the vegetation, collected it into vapor traps using dry ice alcohol slurry at minus 80 degrees, collected all the water out of the air at different heights, and then over hour time frames, collected enough samples to do a Keeling plot analysis. Okay. And there's some examples of the kind of Keeling plots that we were able to generate with such few data and with such crude approaches in the field. And the interesting thing about this project was that the system was dry, the surface was really dry and cleared of understory vegetation for the experiment, and then surface irrigated after a day or two of the project. And so we measured the water vapor isotope profiles before the irrigation event and then several days subsequently to look at this effect of changing surface water availability and its influence on the partitioning of evaporation and transpiration. And this relates back to some of the comments I made earlier about how important this is in agriculture. If this is the way you irrigate your olive orchards in a really dry area, you're going to lose a lot of water to the atmosphere that's wasted because it's not being used by the crop to produce more olive oil. Bad for us, right? So this is a big water resource issue, and many countries in the Mediterranean, including in North Africa, have moved to drip irrigation systems because of the very wasteful ways that this flood irrigation can happen. But we use it as an opportunity to compare partitioning methods, flux methods versus isotope methods, to see how well these methods compared, see if isotope methods were really that powerful. And what you can see is the different Keeling plots we generated for before the irrigation on the top left and then several days after the irrigation. So it looked like it was working. We were developing nice mixing relationships with the atmosphere. And when we did the calculations, we came up with this partitioning pattern. So on the first day before irrigation, because the soil was really, really dry, the signal that we were measuring using the Keeling plots reflected a 100% transpiration source. But after the irrigation, you can see it shifted as evaporation from that flood irrigation contributed to the total evapotranspiration flux of the system. So the evapotranspiration flux went up, but the transpiration rate stayed about constant. And we measured this using sap flow methods. And so the increase in evapotranspiration was due to the evaporation off the wet soil surfaces. And note that the values increased with time, which was kind of surprising to us. We'd assumed that as the soil wetness was depleted and began to dry out, that we would see a reduction in the contribution of evaporation versus transpiration over the course of these days. But when we looked at the meteorological record, we also noted that over the several-day period that the energy driving evaporation was increasing as the temperatures warmed and the air dried over that week period. So the explanation there is that the soil surface remained wet for the entire week, but the energy to drive evaporation increasing the proportion of evaporation to transpiration in that olive orchard. So it looked to be quite powerful, but we didn't have any way to sort of check these measurements to know how, or were we on scale? I mean, was this a reasonable estimate of evaporation and transpiration? Yeah.
Could it also be due to the type of irrigation? Because you showed furrow irrigation, I think.
Well,
water will take time to distribute
it happens quite quickly. They do this in just a few hours. The workers go into the field, they send water down these drainages, and they use little olive branch check dams to route the water into these paddocks. The water goes entire, yes, and so it's well distributed throughout the whole footprint area of our measurement within several hours, and so they did this quite rapidly. Okay, so we compared the isotope method with another method. We measured sap flow in olive trees, which only measures transpiration, and then associated with that we have an eddy flux tower to measure total evapotranspiration. So using this other more traditional method, we could partition E and T and compare to the isotope method. We had to be aware of the flux footprint and the different types of olive architecture. The trees, some trees were young, some were older, some were multi-stemmed, and we accounted for that variability in our sap flow measurements. And using the flux footprint, we were able to then match the eddy flux tower to the sap flow estimates for each of the trees in that footprint. And then these are some of the results, and what this shows you is that on the y-axis, the transpiration rate or the soil evaporation rate estimated by either sap flow and eddy covariance methods in the open symbols, or estimated from the isotope Keeling plots in the closed symbols. And you can see during this midday time period, it worked really well, that the estimates were dead on. At least they were very comparable between the methods, which gave us confidence about using this isotope approach to partition E and T. I might say that later in the day, it didn't work as well, probably because we didn't account for the non-steady state transpiration conditions of the olive well enough in the system. Okay, so take home from that section on E and T partitioning, are there any questions? Okay, good. I'm happy about that.